Welcome to this lecture. Before we begin, may I please make a few remarks? I have now been a teacher for 58 years, and it has always been standing in front of the blackboard, writing on it with the students right in front of me. The real-time interaction between me and the students has been extremely important for my lectures. This is not possible in online lectures such as this one. But YouTube does offer scope for some feedback. You can write your comments and share your reactions on my lectures. After all, this will help me to prepare the lectures in a manner that will benefit you even more. So please do share your comments with me. Thank you very much. Now let us begin with the topic of this lecture, the 10th in the series. The topic of today's lecture is quantum statistics. In particular, Fermi-Dirac statistics, which is obeyed by electrons, neutrons, protons, and other particles. But before we begin, let me make a few introductory remarks. First of all, what is the equation of state? The equation of state is the relation between the pressure of the gas and its density and temperature. The equation of state depends upon whether the gas obeys classical statistics or quantum statistics. What do we mean by statistics? What we mean is the following. A statistical distribution tells you how the various energy levels are populated. In particular, what will be the ratio of the population in two energy levels, say E1 and E2. This equation of state plays a crucial role in the life history of stars, as well as in the end states of stars, the white dwarfs and the neutron stars, which we shall discuss in considerable detail in the following lectures. First, let us discuss briefly what is the classical statistical distribution, which was discovered by Maxwell and Boltzmann in the mid-19th century. What Maxwell and Boltzmann said was the following. If E is the energy levels of the particle, or energies of the particle, then the probability that a state with an energy E is occupied is proportional to exponential to the power minus E over kT. So this is the probability distribution. Now if I give you N particles and M energy levels and ask how will the particles be distributed amongst the various energy levels, and that is given in classical statistics by this expression. The number of particles with energy between E and E plus dE is proportional to E to the power minus E over kT multiplied by square root of E dE. This factor square root of E dE is merely the number of states with energies between E and E plus dE, also known as the density of states. So this first expression is the probability that a particular level is occupied, and the second is the number of particles in each energy levels. Pictorially, this distribution function n of E dE as a function of the energy E is given by this bell-shaped curve. This is the Maxwell-Boltzmann distribution of classical physics. Now what this tells you in the bottom is, if I give you a set of particles and a set of energy levels, how will you populate it? At absolute zero of temperature, for example, in classical statistics, you are allowed to put all the particles in the 0th energy level. But as you warm the gas, more and more of the higher levels will be occupied, and this distribution is an exponential distribution. So just as the density of our atmosphere decreases exponentially, similarly the number of particles in higher energy levels decreases exponentially. So that is a 2-minute summary of classical statistics due to Maxwell and Boltzmann. So now we turn to quantum statistics. Before we come to quantum statistics, let us briefly recall the essential new features of quantum physics. The most important thing is what was discovered by the French physicist Louis de Broglie. He said, just as light, which is normally considered as a wave, also behaves as particles, which we now call as photons. This was asserted by Einstein in his explanation of the photoelectric effect. De Broglie asserted that every particle also behaves like a wave. Just as the wave behaves like particles, particles also behave like waves. This is the duality principle which underlies quantum physics. The de Broglie wavelength, in other words, if I consider an electron or a neutron or a proton, I can ask, if you say it is a wave, what will be its wavelength? The wavelength is given by Planck's constant divided by the momentum of the particle. This is exactly the relation for light also. The momentum of a photon, P, is lambda with the Planck's constant divided by the wavelength, or h nu divided by c, where nu is the frequency. So what de Broglie said, which was an unbelievably revolutionary statement at the time, is particles behave like waves just as light behaves like a particle. Now each wave is described by a mathematical function which is known as a wave function. Now each quantum state of a particle represents a system of standing waves, such as this. So if I have a string tied at these two ends, 0 and L, if I pluck it anywhere, it will vibrate in an arbitrary fashion. But the only waves that will survive are these fundamentals and these harmonics, because these will form standing waves. Same is true of quantum waves. Now these waves, or the wave function, satisfies a differential equation which was discovered by Erwin Schrödinger and is known as Schrödinger equation. Some of you may have studied this in your college. Now, one of the fundamental principles of quantum physics is that energy levels are always discrete. For example, if I consider a particle, and let's say an electron, inside a box of length L, a one-dimensional box, then its energy levels are discrete and are given by E1, E2, E3, E4, and so on. Now, what are the values of these energy levels? If you solve Schrödinger equation, then you get the expression. The energy of the nth level is n squared h squared divided by 8m L squared, where L is the length of the box, in this case a one-dimensional box. Where do you get this expression from? By solving Schrödinger equation for a particle in a box. Now notice that this expression is very different from the expression for the energy level of an electron in a hydrogen atom. In an electron in a hydrogen atom, the energy level, the nth state, is proportional to 1 over n squared, where n is 1, 2, 3, 4, and so on, the principal quantum number. In the case of a particle in the box, the energy levels are proportional to n squared. Therefore, the spacing between successive energy levels increases, whereas in a hydrogen atom, the spacing decreases. Equally important is that the energy of any given level is inversely proportional to 1 over the square of the length of the box. So if I make the box smaller, then the energy will get larger. This is true for every single energy level. A fundamental principle of quantum mechanics is Heisenberg's uncertainty principle, which he discovered 2 years after de Broglie's paper in 1927. What Heisenberg stated was this. He said that one cannot determine both the position and momentum of a particle with infinite precision, which you could do in classical physics, where particles were point particles. Because particles are wave, you cannot do that. One is allowed to determine one of them, either the position or the momentum, extremely accurately, but at the expense of error in the measurement of the other. Now, suppose the position and momenta are denoted by variables x and p, and if delta p and delta x are errors in the measurement. What do you mean by errors in the measurement? If I do the measurement n times, I don't get the same value. There is a certain distribution, and that distribution has a certain width, which is characterized by the standard deviation. That standard deviation is the square root of delta p squared. Now, what Heisenberg's uncertainty principle says is that the standard deviation in the measurement of the momentum multiplied by the standard deviation in the measurement of the position must be greater than Planck's constant divided by 2. That's the same expression. What this means for us is the following. Now I have a particle in a box. So I know the particle, I don't know the position of the particle inside the box, but I know that it is at least inside the box. So it's somewhere between 0 and L. But if I now squeeze the box to a smaller dimension, then I know its position better. So what Heisenberg says, yes, you know the position better, but your uncertainty in the measurement of the momentum will become larger, so that delta p times delta x is still greater than h by 2. Now this motion of the particle has nothing to do with heat. It is a direct consequence of the Heisenberg's uncertainty principle. So if you confine a particle to smaller and smaller dimensions, you can do so only by virtue of giving the particle larger and larger momentum. This motion, which arises from Heisenberg's uncertainty principle, is known as zero-point motion. There are 3 important differences from classical statistical mechanics in quantum statistical mechanics. Those 3 differences are the following. In classical statistics, if I give you 5 electrons or 5 protons, then the electrons are distinguishable from one another. In other words, I can label the electron 1, 2, 3, 4, and 5. So the 5th electron is distinguishable from the first or the second electron. You can't do that in quantum statistics. The particles are indistinguishable. The second thing is momentum space is no longer continuous. In classical physics, momentum can take all values, but in quantum mechanics, it can take only discrete values, and therefore the momentum space is made up of little blocks, like little bricks, cubical bricks, and this is a consequence of Heisenberg's uncertainty principle. And the third is that the particles, all elementary particles, have intrinsic angular momentum. In other words, they have angular momentum even if they are not spinning about their axis or going around something else. So it's an intrinsic angular momentum. So let's understand each one of these 3 a little more. First, let us consider particles of the same species. I give you 2 red particles and a blue particle. In classical physics, I can name the red particles R1 and R2. So I can have a configuration, this is R1, this is R2, and this is the blue particle. But I can also put R2 here and R1 there. But you can't do that in quantum physics. Therefore, in quantum physics, the only configurations that are allowed are either this, or this, or this, because this R and this R are indistinguishable. What do I mean by saying momentum space is discrete? Now let us consider momentum space with three axes, momentum along the x-axis, y-axis, and the z-axis. In classical physics, all momentum values are allowed. For example, if I consider a sphere of a certain radius, which is p, where p is square root of px squared plus py squared plus pz squared, then every value of the momentum inside the sphere is allowed in classical physics. But in quantum physics, you cannot do this. Momentum values are discrete. Why are momentum values discrete? Because the moment I put a particle inside a box of size L, then the uncertainty in the momentum is given by h divided by L, because delta P, delta x must be equal to h bar by 2. Therefore, there is an uncertainty in momentum arising simply by virtue of the fact that the particle is in a box of length L. Therefore, what is the volume of this elementary brick of momentum space? It is h by L into h by L into h by L for the three dimensions, or h cubed divided by v, where v is the volume of the box in which the electron or the proton or the neutron is. So please understand, the discreteness of momentum space is a direct consequence of Heisenberg's uncertainty principle. So momentum space is not continuous, it is made up of little Lego blocks such as this. Third is particles have intrinsic angular momentum. Now all elementary particles have intrinsic angular momentum, regardless of whether they are going around the nucleus or what have you. Why should they have this intrinsic angular momentum? Well, why should the elementary particles have a mass? Why should some elementary particles have a charge? Nature has bestowed these properties on the particle. Similarly, it is the law of nature that every particle possesses an intrinsic angular momentum. We still don't understand very deeply why this is so, but it is so. The intrinsic angular momentum is also referred to as the spin angular momentum, or simply spin. Now, the spin angular momentum of elementary particles takes on or can take on the following values. The spin angular momentum is given by s times h bar, where h bar is h divided by 2 pi. And s is the quantum number which can take on values 0, 1 half, 1, 3 halves, 2, 5 halves, 3, and so on. So therefore, there are two kinds of particles. Something has gone wrong with the color here. The wave function of a system. So why are there two kinds of particles with spin angular momentum, which are either multiples of Planck's constant, 0, 1, 2, 3, or half integral multiples, half, 3 halves, 5 halves, 7 halves, and so on? That has to do with the fact that depending on the statistics obeyed by the particles, if I interchange two particles, then the wave function either remains symmetrical with respect to this exchange or is anti-symmetrical with respect to this exchange. So the wave function of a system of identical half-integer spin particles changes sign. In other words, it's anti-symmetric. This is true, for example, for electrons. But particles with wave function which are symmetric are called bosons. I apologize. I don't know what has gone wrong. I made these slides with my laptop and now using my desktop. So they have different versions of PowerPoint and therefore the colors have gone wrong. In other words, there is a theorem in physics which is called the spin statistics theorem that states the integer spin particles obey the statistics due to Bose and Einstein. These particles are called bosons, while half-integer spin particles are called fermions, and they obey the statistics of Fermi and Dirac. So, spin angular momentum, to repeat once again, can take on values 0, half, 1, 3 halves, 2, 5 halves, and so on, multiplied by Planck's constant divided by 2 pi. Particles with spin 0, 1, 2, etc. obey Bose-Einstein statistics and they are called bosons. Particles with spin half, 3 halves, 5 halves, etc. obey the rules of Fermi and Dirac, the Fermi-Dirac statistics, which we are going to discuss now. These are called fermions. But Fermi-Dirac particles like electrons, protons, neutrons, etc. also have to obey Pauli's exclusion principle, which says that in any quantum state, you can only have one particle. This relation between spin and statistics was first discovered by Wolfgang Pauli around 1940. Now let's look at some of the elementary particles. Electrons, positrons, neutrino, protons, neutrons, and so on obey Fermi-Dirac statistics, and their spin angular momentums are half-integral particles. But there are other particles like pi mesons, k mesons, photons, gravitons, which have not yet been discovered. They obey Bose-Einstein statistics because their spin angular momentum is an integral multiple of Planck's constant divided by 2 pi. Having given you this brief introduction to quantum statistics, we shall now concentrate exclusively on Fermi-Dirac statistics, which is the statistics obeyed by particles such as electrons, protons, neutrons, and a few other particles. But in the context of stars, which is what we're going to discuss starting in the next lecture, we are mainly concerned with ordinary matter, which consists of protons, neutrons, and electrons. Now, what is the Fermi-Dirac distribution? It is the distribution which tells you what is the probability that a state with an energy k is occupied. And what Fermi-Dirac statistics says is that this probability distribution is given by 1 divided by exponential to the power e subscript k minus mu divided by kt plus 1, where mu, which we shall discuss in detail in a minute, is known as the chemical potential. There is nothing special about quantum statistics. In classical statistics also, this concept of chemical potential is there. This is the probability distribution. Now, suppose I have a series of energy levels, K1, K2, K3, and so on, and I put particles in various energy levels according to this probability. Then I ask, what is the total number of particles in all these energy levels? That is simply a summation over all energy levels k of this probability distribution f of ek, or summation over k of this distribution function, and that must simply be equal to the total number of particles that I gave you to populate amongst these energy levels. Now, let us consider Fermi gas of elementary particles, let us say specifically Fermi gas of electrons. Now let me recall for you what I said a few minutes ago, namely that momentum space is discrete because of the wave nature of the particle and Heisenberg's uncertainty principle. Now let us consider a momentum vector whose value is p subscript f for p subscript Fermi. This is known as the Fermi momentum. Let us consider a sphere whose volume is 4 pi by 3 pf cubed. Now in quantum statistics, this is built up with a whole lot of Lego blocks, with each block having a volume h cubed divided by the volume of the substance. Now, although Pauli's exclusion principle, which has to be obeyed by electron, says that you can only put one particle in each quantum level, because the electrons have spin angular momentum, which can either be plus 1/2 or minus 1/2, Pauli does allow you to put two particles in each quantum state, provided you're careful enough to make sure that the spin angular momentum orientation are not the same. They have to be anti-parallel. You are allowed to do this without violating Pauli's exclusion principle. Now let's go back to this expression, which tells you that the total number of Fermi particles is simply given by the summation of 1 over e to the power e minus mu over kt plus 1 summed over all energy levels. Now we can convert this summation to an integral if the energy level spacings are very, very small. Now the energy level spacing, I told you, for example, particle in a box is proportional to 1 over the square of the volume of the box. Therefore, as the volume of the box increases, if you're considering a macroscopic volume, then the energy levels are very closely spaced, and therefore you can convert the spin to an integral. Now, I won't bother you with all the mathematical details. I shall simply say that when I convert a discrete summation to an integral, what comes in the integral, which is integral from 0 to infinity, over the energy, is not only the probability distribution which we are summing, but the square root of E factor that I alluded to before when I showed you the Maxwell-Boltzmann distribution. That simply tells you, square root of E simply tells you the number of energy levels between E and E plus dE. So it is simply a trick to convert summation to an integral. You have to multiply it by the density of states. Don't bother about all these constants that come from this density of states. Now, let us absorb all these constants and call it C. So what I want you to remember that in Fermi-Dirac statistics, the total number of particles in a volume V is equal to the integral from 0 to infinity of the probability that an energy level E is occupied multiplied by the number of levels between the energy E and E plus dE integrated over all energy from 0 to infinity, and of course this is the constant C which we know precisely. Now let us recall the corresponding expression. Before that, let us now ask, what is the total energy of the electron gas? The total energy of the electron gas is simply calculated as follows. Now imagine that you own an apartment building, which is a skyscraper, consisting of many floors. You are the landlord. How much total rent do you collect? Well, this is the total rent you will collect. That is equal to the summation over all the floors of the rent for a floor, which is the eth floor, that is the rent, the number of floors, number of apartments in that floor, which is N of E dE. In other words, let's look at this expression. Let me say this once again because I think I didn't state it very clearly. As the landlord, this is the rent that you will collect. Let us consider a particular floor where for each flat the rent per month is E. But there is no guarantee that this floor is occupied. Therefore, you have to multiply by the probability that this floor is occupied or this energy level is occupied. Now, in that floor, let's call it the 25th floor, if it is occupied, then you have to collect rent from all the flats that are occupied in that floor. And how many flats are there occupied in that floor? It is square root of EDE. So this is the rent that you will collect from each floor, and that integral will give you the total rent that you will collect from the skyscraper that you own. Same is true for the total energy of an electron gas. The total energy is the integral over all energy values of the energy of the particle multiplied by the probability that the energy level is occupied multiplied by the number of energy levels between E and E plus dE integrated over all energy values. Now, since the electron gas has a total energy, it will exert a pressure, because according to thermodynamics, the pressure of a gas is simply 2 by 3 times energy density of the gas, namely total energy divided by the volume. Therefore, just as a classical gas which obeys Boyle's law exerts pressure, which is simply given by 2 by 3 energy density of the classical gas, in a similar fashion, a quantum gas of electrons will exert pressure, and that pressure is simply 2 by 3 times this total energy of the electron gas divided by the volume of the box. That is what I have written there. So you will say, what is the big deal? A classical gas has pressure. Similarly, a quantum gas has a pressure because a quantum gas has internal energy. After all, I am populating electrons in various energy levels. Similarly, a classical gas can have various speeds and various velocities. Therefore, this is no big deal. But you will see why it is a big deal very soon. Now let us remember Maxwell-Boltzmann distribution. According to the classical statistics of Maxwell and Boltzmann, the number of particles with energy between E and E plus dE is proportional to exponential to the power minus E over kT, which is the probability that an energy level with value E is occupied, multiplied by the density of states, which is square root of E dE. What is it in Fermi-Dirac statistics? NEDE is some constant, which we have not written here either. This probability distribution is now different. Instead of exponential to the power minus E over kT, it is 1 divided by exponential to the power E minus mu over kT plus 1. As I shall refer to in a moment, under certain circumstances, for example, when the temperature is very high and if the density of particles is very low, this one can be neglected in comparison to the second term, and this exponential can be taken upstairs and it will become e to the power minus E over kT, which is the same as Maxwell-Boltzmann distribution. Therefore, in the limit of high temperatures and low densities, for reasons that I shall now mention, quantum statistics of Fermi and Dirac reduces to the familiar Maxwell-Boltzmann statistics. This is known as the classical limit. Now, why is there a classical limit? What happens to quantum mechanics? Is quantum mechanics wrong? No, it's not quantum mechanics is wrong, but quantum mechanics is making unnecessary fuss under certain limiting condition. What is this unnecessary fuss? For example, for a given temperature, when the gas density is very, very low, then the number of particles in any given energy level will be rather small, because total number of particles itself is rather small. Then the interaction between the atoms and molecules or electrons and protons or what have you is negligible. In this limit, the mean number of particles in any quantum level will be very small compared to 1. Therefore, the overlap of the wave functions of the 2 electrons or 2 protons or 2 neutrons will not be very relevant. And when the wave functions of the two particles do not overlap very much, you don't have to worry about whether the wave functions are symmetric with respect to exchange or anti-symmetric with respect to exchange, and therefore Pauli's exclusion principle is not going to be important. In this limit, where Pauli's exclusion principle or the exchange effect will not be important, in that limit, quantum statistics will go over to Boltzmann statistics. And that limit is simply that the mean number of particles in any quantum level is very small compared to 1. Now, you will say, for a given temperature when the density is low. But I told you in one of the early lectures that in physics, it's meaningless to say high or low. Things have to be in comparison with something or other. Similarly, you can't say low temperature or high temperature. It has to be in comparison with something else. You're absolutely right. So I will tell you exactly how to view this classical limit. The classical limit is really a comparison between the quantum energy of the particle, the characteristic quantum energy of the particle, which is the Fermi energy, which we shall define presently, and the thermal energy of the particle, which according to classical statistics is simply kT or 3/2 kT. So I haven't told you yet what this Fermi energy is. I shall do that presently. But please know that it's really not comparing apples and oranges by saying high or low temperature, high or low density. What I am really comparing is the characteristic energy of the particle according to the rules of quantum physics, which is EF, and the characteristic energy of the particle according to classical physics, which is kT. So when quantum energy is very small compared to kT, then the Fermi-Dirac statistics will go over to Boltzmann statistics of classical physics. Now, as we shall see, the Fermi energy of an electron gas is given by h bar squared divided by m multiplied by the number density of particles, the total number divided by the total volume to the power 2 by 3. So this is the Fermi energy, EF, of the electrons or protons or neutrons. Therefore, you see that it is a comparison where this dense characteristic energy in quantum physics, if it is very small compared to kT, then you are dealing with classical statistics. But if kT is very small compared to EF, then you have to describe the particles according to quantum statistics. Now, what is the typical value of this Fermi energy of an electron gas? Do we know of electron gas? We know there are electrons in atoms and molecules, but what is this electron gas that you're talking about? We know that metals conduct electricity. They conduct electricity because there are free electrons. The valence electrons are not tied to individual nuclei, but they move the common property of all the nuclei. It is this free electron gas that enables electrical conduction in metals. So if you now go to a simple book on solid-state physics like Kittel's solid-state physics, you will find a table such as this listing the value of Fermi energy for various metals. Here are some familiar metals. Sodium, it's 3.24 electron volts, and in potassium, it's 2 electron volts, and in some of the heavier elements like cobalt and so on, it's about 10 electron volt. Now please remember that 1 electron volt in temperature unit is approximately 10 to the power 4 Kelvin. In other words, Boltzmann's constant K subscript B multiplied by 10 to the power 4 Kelvin is 1 electron volt. Therefore, what we are saying is that the Fermi energy of metals in temperature units corresponds to several tens of thousands of degrees. Several tens of thousands of degrees. Now, so the Fermi energy of various metals is larger than 10,000 degrees. For example, for cobalt, it's 10 to the power 5 Kelvin. What is this to be compared with? The temperature of sodium or copper or nickel, which is 300 Kelvin. Therefore, you see that the characteristic quantum temperature, or which is simply the Fermi energy divided by Boltzmann's constant, is very large compared to the temperature of the metal. That is why electrons and metals have to be described not by classical statistics, but by Fermi-Dirac statistics. Therefore, electrons and metals are highly degenerate and they have to be described by Fermi-Dirac statistics. Now, let us look at the central density of the Sun. The central density of the Sun, the average density of the Sun is just the density of water, 1.4 grams per cubic centimeter. Whereas the central density of the Sun is 150 grams per cubic centimeter. So you would say, therefore, the electrons in the center of the Sun must be degenerate, because after all, electrons in a metal whose density is only 4 or 5 or 6 are degenerate. No, but that's not true, because the metals are at a temperature of 300 Kelvin, whereas the central temperature of the Sun is 15 million degrees. So if you actually compute KT and the Fermi energy, which I urge you to do as a very small exercise, using the formula that I will give again and again and again, you will find that KT is very large at the center of the Sun compared to EF. In other words, the thermal energy of the electrons, KT or 3/2 KT, is very large compared to the characteristic quantum energy, which is EF. And therefore, electrons and protons and neutrons at the center of the Sun will obey Boyle's law, which is the equation of state for a classical ideal gas. But as we shall see in the next lecture, when we begin to discuss the evolution of stars, as the star evolves, the density, the central region will contract and the density will increase substantially. When the density increases, this inequality will be violated. KT will no longer be greater than EF. KT will become less and much less than EF, and the gas will become quantum or degenerate. Now, this transition from classical behavior to quantum behavior has a very profound effect on the evolution of the Sun, as we shall see in the next lecture, which is the justification really for my digression from astronomy into statistical mechanics. So this, what I am discussing now, is extremely important. Indeed, as we shall see, it's a matter of life or death under certain circumstances. Now, let us discuss a Fermi gas at absolute zero of temperature. Now, as I told you before, in classical physics, at a finite temperature, there is thermal motion. The average energy of the particles is kT, or 3/2 kT. So when temperature is zero, all motion cease. This is why you are allowed to put all particles in the lowest energy level in Maxwell-Boltzmann statistics, if you remember the slide that I showed you. And of course, there is no restriction coming from Pauli's exclusion principle, because you are dealing with classical particles and classical physics. Now, you told me that, well, what's the big deal about the quantum gas? It has energy, therefore it has pressure, just as the classical gas has various velocities and speeds, and therefore it has energy and pressure. But let's look at it at zero temperature. So these are the various energy levels of an electron in a box, in a sample of a certain volume. Now, according to Fermi-Dirac statistics, this is the way you will populate your flat in your skyscraper. You will put 2 electrons with their opposite spin in the first level, 2 in the second level, 2 in the third level, and so on, till you run out of electrons. And that highest energy the electron has is known as the Fermi energy. So all flats in your skyscraper up to that floor are occupied, and all flats above that are empty. Now you may say, but look, why can't I do this? Yes, you can do that, but this will have a higher energy than this. And thermodynamics tells you that the most stable configuration is the one with the lowest energy. Therefore, the lowest energy configuration of a set of n electrons in a volume V is what is shown on the left. You put 2 electrons with opposite spin in each energy level till you run out of electron. And that highest energy level is known as the Fermi energy. So, is that the average energy of these particles? No, it is some fraction. So, the rent of each floor is different, but the average rent is roughly some 3/2 or 1/2 or 1/4 of the maximum rent that you are going to collect. In a similar fashion, the average energy of this particle will be some fraction of the maximum energy. As it will turn out, it is actually 3/5 times the maximum energy. But we shall consider 3/5 as 1. So it is in this sense that I said that the characteristic quantum energy is EF, which is the maximum energy up to which all levels are occupied at absolute zero and all levels are unoccupied at absolute zero. Now let us introduce the notion of Fermi momentum, and let us actually derive the expression for the Fermi momentum. Now, we know that this momentum space is built up of little Lego blocks, cubes. The volume of each cube is h cube divided by the volume. Where did this come from? Uncertainty principle tells you that the side of each of these is h by L into h by L into h by L, which is h cube divided by the volume. The volume of the sphere, which is fully occupied, is 4/3 pf cubed. So all states inside are occupied and all states outside are empty at t equal to 0. Now, how many electrons are there in this sphere? Well, you have been careful to put 2 electrons in each apartment, provided the spins are anti-parallel. Therefore, the total number of electrons in this occupied sphere is the number of apartments multiplied by 2 tenants in each apartment. Therefore, it is this expression on the top multiplied by 2. 2 comes from 2 electrons or 2 protons or 2 neutrons in each momentum state or each energy state. So if you simplify this expression, you get the following expression for the Fermi momentum. The important thing to appreciate is that the Fermi momentum is proportional to density of particles to the power 1/3. Density of particles to the power 1/3. That is the same thing over there. Now please notice that the mass of the elementary particle does not enter this Fermi momentum expression. It comes simply from the discreteness of momentum space comes only from uncertainty principle, and that has to be satisfied by electrons, protons, neutrons, or what have you. Therefore, the mass of the particle will not be enter into this formula. Therefore, if I give you a set of electrons or protons and neutrons, if the number are the same, then the Fermi momentum of the electrons and the Fermi momentum of neutrons and protons will be the same as long as the density of the particles remains the same. So if I now have a box of electrons with n electrons in a volume V, and I compress that box to a smaller volume, what will happen? The radius of the occupied sphere at absolute zero will increase because the Fermi momentum will increase as n by v to the power 1 by 3. Since volume is smaller, the density is larger, therefore the Fermi momentum of this configuration is larger than the Fermi momentum of that configuration. So as the density increases, the maximum momentum will increase. Now we can define the Fermi energy. Let us say that the particles are moving at speeds which are very small compared to the speed of light. Then Newtonian mechanics is valid. According to Newtonian mechanics, the energy of a particle, the kinetic energy of the particle, which is half mv squared, is p squared divided by 2m. Therefore, the Fermi energy of a particle is pf squared divided by 2m, where pf is the Fermi momentum. So, I use the expression for the Fermi momentum from the previous slide, which is over there with a suitable constant of proportionality. Then I get the Fermi energy is equal to all these things multiplied by density to the power 2 by 3. Why do 2 by 3? The Fermi momentum is proportional to density to the power 1 by 3. Therefore, the square of the Fermi momentum is proportional to density to the power 2 by 3. Please notice this important thing. And other thing to appreciate is Fermi energy does depend upon the mass of the particle in Newtonian mechanics. The Fermi momentum did not depend upon the momentum of the particle, but the Fermi energy depends on the mass of the particle. Why does it depend upon the mass of the particle? Because in Newtonian mechanics, energy is p squared divided by 2m. Therefore, if I give you the same number of electrons and protons and neutrons, whereas the Fermi momentum will be the same numerically, the Fermi energies will be very different. For example, the Fermi energy of the neutrons and protons will be 2,000 times less than the Fermi energy of the electrons, because the mass of the proton and the mass of the neutron is 2,000 times the mass of the electron, and the mass comes in the denominator. Therefore, if I now consider a gas of electrons or protons and neutrons and compress it to a smaller volume, then the maximum energy will also increase. It will increase by density to the power 2 by 3. So to summarize, as I compress an electron gas, the Fermi momentum will increase as density to the power 1 by 3. The Fermi energy will increase by density to the power 2 by 3, as long as the gas obeys Newtonian mechanics, which it will do if it is not relativistic, or in other words, if the speeds are small compared to the speed of light. Now, what does this distribution function look like at absolute zero of temperature? Now, in the case of Maxwell-Boltzmann statistics, I told you the distribution is an exponential distribution. Here at finite temperature, the distribution function is what is shown in this yellow box. It is 1 divided by e to the power e minus mu divided by kt plus 1. Now please take a piece of paper and convince yourself that if I put t equal to 0, I will get the following remarkable result. As long as I am less than the value of this chemical potential at absolute zero of temperature, which is given the name the Fermi energy, as long as the energy is less than mu, then E minus mu will be negative. Therefore, if I divide by 0 here, then it will be e to the power minus infinity, which is 0, and 1 by 1 is just unity. Whereas if e is greater than mu, then at t equal to 0, it is e to the power infinity, which is infinity. Therefore, f of e is 0. Therefore, you have this beautiful step function. What is it trying to tell you? It tells you the same thing that I showed in the earlier picture. It tells you that the probability that the energy levels are occupied is 1 certainty. So I'm putting 2 electrons, 2 electrons, 2 electrons, 2 electrons, till I run out of electron, and that maximum energy is the Fermi energy, and the probability of occupancy above that is 0. And this I've already assumed in my diagrams in the earlier slide. The momentum space was occupied up to the Fermi momentum. Everything was empty beyond that. Let us now therefore calculate the ground state energy at absolute zero of temperature. Now the ground state energy is to be calculated according to this. This is the same old formula which we use to calculate the total rent you're going to collect from all your tenants in your skyscraper building. The total rent you'll collect is the rent from each flat in a particular floor. The probability that the flat is occupied multiplied by the number of flats in that floor integrated over all floors from 0 to infinity. And the expression for f of E is now explicitly written, and the density of states is square root of E dE with all these constants sitting in front. Now, at absolute zero of temperature, I know that this integral from 0 to infinity reduces to an integral from 0 to EF. Why? Because this function inside the integrand, the probability function, is unity from 0 to EF and 0 beyond EF. Therefore, this integral cuts off at the Fermi energy EF. And up to the Fermi energy, its value is unity. Therefore, the integrand is E times square root of E, which is E to the power 3 by 2. This is the same formula as before. Therefore, that is an elementary integral. Therefore, the total energy of an electron gas is equal to all these constants multiplied by EF to the power 5 by 2. The total energy is given by this expression over there. There's the same thing over there. I have written explicitly what the Fermi energy is. The Fermi energy is given by all these things. And there is an extra n there because the way I have written it. If I simplify this, I get density to the power 5 by 3. Therefore, the total energy of an electron gas at absolute zero of temperature is density to the power 5 by 3. The first and foremost thing to appreciate is that this total energy is not zero. In classical physics, the total energy of the gas is zero because each and every particle has zero energy. All motions have ceased. In quantum physics, motions have not ceased at absolute zero of temperature because in order to not to violate Heisenberg's uncertainty principle and Pauli's exclusion principle, I must, as I compress the gas to a certain volume, give it more and more energy, and therefore particles have a total energy at absolute zero of temperature, and the average energy of the particle is total energy divided by n, which is 3 by 5 times Fermi energy. Don't worry about the 3 by 5. You remember the average energy of a quantum particle at absolute zero of temperature or even at finite temperature is of the order of the Fermi energy EF, which is proportional to density to the power 2 by 3. Now, because the electron gas has total energy at absolute zero, it will exert pressure, because the pressure is nothing but 2 by 3 times the total internal energy divided by the volume. Now, remember how we calculated Boyle's law. The internal energy is the average energy of the particle multiplied by the total number. the total number of particles is 3 and the average energy is 3/2 kT, and that gave me pressure is nkt, which is Boyle's law. We'll do the same thing to calculate the pressure of the Fermi gas at absolute zero of temperature. Here is the expression for the internal energy. Therefore, the internal energy is the average energy of the particle multiplied by the total number of particles. The average number of particles is approximately the Fermi energy multiplied by n, that is n into n by v to the power 2 by 3. Therefore, the pressure of an ideal Fermi gas at absolute zero of temperature, which is known as the degeneracy pressure, is density to the power 5 by 3. The density to the power 5 by 3 defines the degeneracy pressure of the electron gas. Why is this gas considered as degenerate? It is a terminology which I have never understood, but all that's trying to tell you is that all states up to the Fermi energy are occupied at absolute zero, and all states above it are unoccupied at absolute zero. So, the most important thing, which will be very important for us when we discuss stars, is that a Fermi gas has non-zero pressure, even at absolute zero of temperature. This pressure arises due to a combination of Heisenberg's uncertainty principle and Pauli's exclusion principle, which forbids you from putting all the particles in the lowest energy level. A Fermi gas has pressure at absolute zero of temperature, and that pressure is very large and it is proportional to density to the power 5 by 3. Now, this pressure does depend upon the mass of the particle. Why does this pressure depend upon the mass of the particle? Because the total energy depends upon the mass of the particle, because we are calculating the total energy in Newtonian mechanics, where the energy of the particle is p squared divided by 2m. Therefore, the mass of the particle does matter when it comes to the exerting the pressure. Whereas, suppose I give you the same number of electrons, protons, and neutrons, they will have the same Fermi momentum, but they will have different Fermi energy because the mass comes in the denominator. In the same way, the pressure exerted by the electron gas will be 2000 times more than the pressure exerted by the neutron gas or a proton gas, because the mass comes in the denominator. This will be very important when we discuss white dwarfs and Chandrasekhar's theory of white dwarfs. The pressure is mainly due to electron, and the pressure of the protons and neutrons can be neglected because it is 2000 times smaller. Now, as I increase the temperature, this step function, which is 1 up to the Fermi energy and 0 beyond it, will get slightly modified. It will develop a small tail. But the width of the tail, or the length of the tail, if you like, will be only of the order of kT. Why is that? Because here is our energy bucket. At absolute zero of temperature, all energies up to this maximum energy EF are occupied, and all energy levels above it are unoccupied. And this maximum energy, Fermi energy, is proportional to density to the power 2 by 3. It is a very large number. For example, for typical metal, it is of the order of 100,000 degrees. Whereas kT is very small because T is only of the order of 300 Kelvin. Therefore, at small temperatures, the thermal excitations will only occur over there. It's only electrons which are over there which can be kicked out of the Fermi sea and taken above this energy level. An electron here cannot be taken over there or there or there because all these energy levels are already occupied. Therefore, Pauli's exclusion principle forbids you from doing anything to these energy levels. So, when I heat Fermi gas from absolute zero to a finite temperature T, nothing much changes. It's only some small number of electrons which are over here will get kicked out of there, and they will acquire normal thermal motions. Therefore, this step function, as I increase the temperature, will develop a tail. Now, as I increase the temperature dramatically, the tail will become longer and longer. When the Fermi energy becomes comparable to kT, the tail will become substantial, and when kT becomes much larger than the Fermi energy, it will become an exponential, which is the Maxwell-Boltzmann distribution. The probability of occupancy is exponential to the power minus E over kT. So this is what I said earlier. So at high enough temperatures, when kT becomes very large compared to the Fermi energy EF, Fermi-Dirac statistics will reduce to Maxwell-Boltzmann statistics. Now, to end this lecture, please permit me a couple of minutes. We should discuss the relativistic Fermi gas. Because when we discuss the theory of white dwarfs and neutron stars and so on, we will be dealing with particles, electrons in particular, whose speeds will be comparable to the speed of light. Now, as far as the Fermi momentum is concerned, I made the remark that the Fermi momentum of the particle does not involve the mass of the particle. This came straight out of Heisenberg's uncertainty principle. Therefore, this formula for the Fermi momentum of the particle will remain valid even for a relativistic electron traveling with a speed very nearly equal to the speed of light. But when we calculated the Fermi energy and the total energy, we assumed that the Fermi energy is Pf squared divided by 2m. You can't do that if the particle is moving with speeds comparable to the speed of light. This relation is valid only in Newtonian mechanics. In relativity, Einstein taught us in 1905 that the relation between the energy and the momentum is not P squared divided by 2m, but the energy is square root of m0 squared c to the power 4 plus p squared c squared, where m0 is the rest mass of the electron. Now, if the particle is moving very nearly at the speed of light, then for such ultra-relativistic particles, then the first term can be neglected. Then the energy of the particle is simply p times c, or momentum times speed. The same is true of photons. The energy of a photon is the momentum of the photon divided by multiplied by the speed of light. The momentum of the photon is h nu divided by c. Therefore, h nu divided by c into c is simply h nu, and we recover Einstein's E is equal to h nu. Similarly, if an electron is moving with speeds very nearly equal to the speed of light, then the relation between energy and momentum is E is pc and not p squared divided by 2m. And that means that the Fermi energy is to be calculated according to the formula Pf into c and not Pf squared divided by 2m. Therefore, the Fermi energy of the particle will remain proportional to density to the power 1 by 3, just as the Fermi momentum was density to the power 1 by 3. In the extreme relativistic case, the mass of the particle does not enter the expression either of the momentum or of the energy. This is as should be. This is what we mean by ultra-relativistic motion. In the world we live in, rest mass energy of the particle is much more than the kinetic energy of the particle. But in the relativistic world, the rest mass energy of the particle is unimportant compared to the kinetic energy. That is what we mean by ultra-relativistic motion. Therefore, the Fermi energy of the particle is proportional to density to the power 1 by 3 in relativistic mechanics. Therefore, the pressure of the relativistic electron gas will also be different. I'm going to skip the details here and say the pressure of the relativistic electron gas will be proportional to density to the power 4 by 3 and not density to the power 5 by 3. And the difference comes simply from the fact that the Fermi energy of the relativistic electron gas is proportional to density to the power 1 by 3 and not density to the power 2 by 3. So let me summarize by saying that an electron gas, even at absolute zero of temperature, possesses and exerts an enormous pressure. And that pressure is proportional to density of the electrons to the power 5 by 3. If the electrons are non-relativistic, it's proportional to density to the power 4 by 3 if the electron gas are relativistic. As we shall see when we discuss the Chandrasekhar limiting mass of white dwarfs, whether the pressure is due to relativistic electrons or non-relativistic electrons is a matter of life or death for the star. With that, I shall conclude this brief review of Fermi-Dirac statistics and the properties of the degenerate electron gas. You might think that this was an unnecessary excursion into basic physics, but as we shall see in the very next lecture, this is extremely important because this governs the evolution of a star. For example, we shall see in the next lecture that stars like the Sun will become giants and supergiants because as the density in the central region increases, the gas will become quantum mechanical and degenerate. So in the next unit of lectures, we shall discuss the life history of stars of various masses, and in the next lecture, we shall discuss the life history of low mass stars. Thank you for your attention, and do share your reactions to these lectures by writing in your comments where the YouTube comments are. Thank you very much.